All right, so now we're going to look at Chapter 9, Inferences from 2 samples. So to recap, first we've learned that we make inferences back to the population based on our measures from a, we hope, representative sample. When we use samples, we're looking at a t-distribution rather than a z-distribution if our samples are less than 120 participants or subjects. So far we've compared one sample to a hypothesized mean. But what if we want to know about potential differences between 2 groups? So the objectives is to conduct a hypothesis test of 2 proportions and 2 means, which are independent samples, and then we're going to do 2 dependent samples. I'm going to skip 9.4 on 2 variances or 2 standard deviations. So when we're comparing proportions, we've already done this when we calculated the sensitivity and specificity, positive predictive value, and negative predictive value. We set up the data the same way in SPSS, but now we're saying that the null is that the probability, which in the hypothesis should be written in Greek because we're hypothesizing about the population, and probability is denoted with pi. So the probability of the first sample is the same as the probability of the second sample. We could also restate the null as 1 minus, or pi of 1 minus the pi of 2, which is 0, right? So if they're the same and you subtract one from the other, it would be 0. The book doesn't use the Greek for this, but it should be the Greek for the null and alternate. I don't like this way as much, so we're going to stick with the equals or not equals. So the alternate hypothesis, the probability of the first sample is not the same as the probability of the second sample, or if we did it this way. Here on out, we're going to stick with 2-sided alternate hypotheses. So in this, one of the examples that I show you, they use a 1-tailed test. We're going to just change it to a 2-tailed test. All right. So let's think about possible research questions this could answer. For example, is the proportion of males and females who exhibit a certain diagnosis equal? Is the proportion of errors in 2 different labs in the same hospital equal? We have assumptions, as we do with all inferential statistics. And for this one, the samples are from 2 simple random samples. That we can't always know, especially if we're handed a data set, but we're just going to assume that that is the case. The samples are independent, so therefore they're not paired. So you can't be in one group and in the other group. You've got to be in one, they have to be mutually exclusive. And for each of the 2 samples, there are at least 5 successes and at least 5 failures. So each cell has to be greater than 5. And these p's should have hats, so p hat, right? But anyway, okay. So the example I'm going to show you is on page 396, example 1. Do airbags save lives? We want to test the claim that the fatality rate of occupants is lower for those with airbags. And in the book, they use the total positives over the total plus the positives. We don't want that. We want those who survived and those who did not survive. So we want to set it up like this in SPSS. So don't use this table, use it this way. You can see that it's they've added 52 to 9801 and they got 9853. We don't want it that way. We want it this way. Anyway, okay, so we'll check our assumptions. We'll assume we have 2 simple random samples. We just say that. We have 2 populations that are independent. You can't be both alive and dead at the same time. And we have at least 5 successes and more than 5 failures. So our null hypothesis states that the proportion of survivals is equal to the proportion of deaths. So those who died is the same as those who survived. Knowing what we know, in reality, in life, people with airbags most likely will survive more often than they will if they didn't have one. So we're probably going to, the book says the alternate hypothesis is that those who survived is greater than those who died. But we're just going to use a 2-sided alternate hypothesis, which says that they're not the same. Okay, so in SPSS, we do the same thing. We have 1 and 2, 3 and 4. These are our cell labels. We did airbag, positive, positive, negative, negative, positive, negative, positive, negative, and then we have the cell counts. So 1 is equal to survive, 2 is equal to died, and 1 is equal to had an airbag, and 2 is equal to did not have an airbag. Okay, so we have to weight the counts. You can never forget to weight the counts. So you go to data, go all the way down to weight cases. You bring over the count and click weight weight cases by frequency variable. We called it count. We say okay. Then we're going to move survival into the rows and airbag into the columns. Then we're going to click statistics. This is something that we have not done before. Before, when we were doing sensitivity and specificity, we just did percentages in the rows and columns. Now we're looking for chi-square, which is the Greek word for the letter X. It's the same in our alphabet as it is in theirs, but we pronounce it chi-square. So we want the chi-square statistic. So we click that one and we click continue. And then we check our output. Okay, here's where it gets a little bit confusing. In the book, they're doing a one-sided test. We are doing a two-sided test. And I'm showing you because you can see both. You can see the one-sided in the text, but I want to show it to you in output because it always gives it to us as a two-sided. You can't really see it's behind the red box, but it says asymptotic significance two-sided. That is our p-value column. That's where we're looking to see if we fail or do not reject or do not reject the null hypothesis. So in order to find a p-value for one-sided, divide this p-value here by 2, and you would get 0.2028. So let me explain what's going on. So a z-score is the square root of the chi-square value. So if I square rooted that, I would get a z-score of 1.91, which is what matches the book. Since they were looking at a left-sided test, it is negative. Remember, way back, we said that plus or minus negative or positive 1.645. That's the critical value. This is bigger than that, so it's significant for a one-sided test. But we're not doing a one-sided test here. We're looking at a two-sided test. So our chi-square value is 3.654, and our p-value is 0.056. Remember, if anything's less than 0.05, it's significant, and here we're not. So it is a non-significant test. We are not going to reject the null hypothesis. Our two-sided test is not significant. The p is greater than 0.05. But if we want to match the book, we divide this by, like I've already said, we divided it by 2 and it would be significant. It just depends on our question and how we phrase our hypotheses. We're not going to worry about confidence intervals for this test. All right, often when we conduct an experiment, we really want to know if there's a difference between the treatment group and the control group on some outcome measure. There are some assumptions that have to be met in order to do this. First, the groups have to be independent of each other. The groups have to also have equal variances, that they come from two similar groups, not widely different groups. This is called homoskedasticity. You don't see it in the book, but it's you may see it in published research. And then also that the data roughly follow a normal distribution. We also have different types of variables. We've talked about this before. We have a variable is a quantity or condition that can change. The independent variable is a variable that you can manipulate or control. The dependent variable, I'm going to add to this, it's also could be a grouping variable. Dependent variable is a variable that you can observe or measure, and a controlled variable is a variable that's kept the same for all conditions. So in the independent samples t-test, this test is used when you have two groups and you want to compare them on some continuous outcome variable. Do you remember our scales of measurement? Nominal, ordinal, interval, and ratio. Our groups are nominal or categorical. Remember, those mean the same thing. And they are the independent variable, which I denote as IV. The outcome or dependent variable, the DV, is the interval or ratio variable that we are observing or measuring. Okay. This is also in SPSS, the interval and ratio is also called scale. So it's a scale variable of interest. We're looking at the outcome of interest for two different groups for an independent samples t-test. Okay, when I was a student, this kind of was confusing to me. So I'm trying to make it as clear as possible and give you sort of a visual as to what's going on. So we've done two tests so far. We've looked at a one sample t-test, and now we're looking at a independent samples t-test, or a two samples t-test. In the first one, we have one group, which is our independent variable, and we're looking at it. We're looking at some outcome measure, the dependent variable, but we're testing it against a hypothesized mean. So is the average number of blood donors during the month of March the same as the hypothesized value? Maybe, you know, from the value from last March. It's just something that we've pulled out of the air. We want to test it against. It could be like average GRE score or average SAT score, something like that for the nation. And I want to see if my group of students is the same or different than that. Now for an independent samples t-test, we have two groups. We have group A and group B, and they're mutually exclusive. You can't be in one and the other. You have to be in one or the other. And we're looking at their comparison on some outcome measure. So the grouping variable is the independent variable, and the outcome measure is the dependent variable. For example, is there a difference in number of blood donors by gender? So we're only looking at two groups. I acknowledge that gender could be non-binary, but for this example, we're just going to look at two groups. Okay, so consider the example on page 417 of the book, number 18, radiation in baby teeth. Listed below are amounts of strontium-90 in millibecquerels, or MBQ, per gram of calcium in a simple random sample of baby teeth obtained by Pennsylvania residents and New York residents born after 1979. Conduct an independent t-test to determine the mean amounts of strontium-90 is greater in Pennsylvania residents than in New York residents. Use alpha 0.05 and report a confidence interval. Okay. In the book, they're calling it an independent t-test, which is fine. In SPSS, they call it independent samples t-test. Just note that difference. Okay, so we're going to do our hypothesis test steps. Number one is to state the hypothesis. The null hypothesis is that the mean of Pennsylvania is equal to the mean of New York for levels of strontium-90 in baby teeth for people born after 1979. The alternate is that they are not the same. So this is a two-tailed test. Set the critical value. This is done for us. It's always 0.05. Not always, but for the purposes of this class, we're going to use 0.05. And then we're going to calculate the test statistic. We're going to use SPSS, and then we'll make our decision. So we want to enter our data into SPSS. And I say here, wait a minute, we have two rows in the book, one for Pennsylvania, one for New York. So we have these values and these values. But here we have two columns. One says strontium-90 levels, and the others have 1 and 2s. Okay, so I have strontium-90, and I put all the values, all 24 of them, into one column because I have to tell the computer which state they're from, right? So I have strontium-90, this is my outcome, this is my dependent variable, and then this is my independent variable. And here I have 1s, which is Pennsylvania, and 2s, which is New York. Okay, so we have to designate a column for each of our variables. I said this. It won't let you use hyphens, so I have to do the underscore. And then we have to go into data view here, click on the little dots. 1 is equal to Pennsylvania, 2 is equal to New York. Okay, so we check our assumptions. The groups are independent of each other. We're just going to assume this is true, that somebody didn't get their measurement in New York and then move to Pennsylvania and get their measurement again. We can't know that, but we're just going to assume. We're going to say that the groups have equal variances. They come from two similar groups, not widely different groups, that homoskedasticity. We're going to test that with the Levine's test. It comes in our output. The null is that there is no difference in variance. So if we reject this, then we need to use the bottom row of output, which I'll show you. The data roughly follow a normal distribution, which we're also going to check. We're going to use the analyze, descriptives, explore, and check normality plots with tests and look at Shapiro-Wilks. The null is that it is normally distributed. All right, so let's check normality first. I go to Analyze, Descriptive to Statistics, come to Explore. I'm going to put my dependent level here in the strontium-90 in the dependent list, and factor list is my other variable, state. I'm going to click Plots. I'm going to click Normality Plots with Tests. And then I get the QQ, right, which we're familiar with. Before we look at our QQ plot and wonder if this was normal enough, but now we know about p-values and the hypothesis testing, and we can actually test this. We will use the Shapiro-Wilk test, which, if not significant, means the variable is normally distributed. So typically we want to see things that are significant. It's exciting. Ooh, there is a difference between males and females. What does that mean? But here we don't want to have significance, because then it means that they are the same, and we want these guys to be the same. So here we can see that for Pennsylvania and New York, they're both greater than 0.05. They're normally distributed. So we meet that assumption. Okay. The next thing we need to do is actually do the independent samples t-test. So we go to Analyze, we come down to Compare Means, and we go to Independent Samples t-test. And here's where the different versions of SPSS have changed. So I will intersperse the new version and keep the old version where I can. So we go to Analyze, Compare Means, Independent Samples t-test. See these little question marks? You need to tell SPSS how you labeled your two groups. It's auto-populated with 1 and 2. But if you use 0 and 1, you'll have to change it. But it won't let you move forward until you check it. So it's here, you just click Define Groups. This will pop up, and then you can just click OK and move forward. And then you get output. And again, the output's a little different than it used to be. So we can see that the mean strontium levels, 90 levels, are larger for Pennsylvania than New York. The standard deviation for Pennsylvania is double that of New York, implying that there's more variability in the sample for Pennsylvania. So let's check our assumptions first. First, we know that the samples are independent because one set comes from Pennsylvania and the other comes from New York. We check the normality and we know that they're both normal. Lastly, we need to check. We see here we have to come to this Levine's test, and look, we have to consider this as its own box because we have an F and then we have the T. The F statistic is what they use to test Levine's. It's just a different test statistic. We'll learn it later. Right now we have a pretty large F statistic and we have significance. What does that mean? That means that equal variances cannot be assumed because the null hypothesis is that they are the same. If we reject a null, then we say they're different. So what do? We're not dead in the water. We have two rows here, right? So if the variances were the same, we'd stay in the top row, but they're not. So we go in the bottom row. So these two samples, if they had, I just said this, if we had equal variances, we would see that Levine's test is not sig, but here it is. So we violate this assumption. So we have to drop to this bottom row, okay? And we come and we look at the equal variances not assumed row in red. Overall, the differences between equal variances assumed and equal variances not assumed are negligible, but it is important that you understand the differences between the two. And I'm going to say this, in your quiz, you will need to know which row to look at. It will be an important part of your quiz. So you need to know to look at this first, evaluate this box first. If this is significant, you drop to this row. If it is not significant, you stay in the top row. So here we see 0.005 for the two-sided P, 0.002 for the one-sided P. They're both significant, right? We're just doing a two-sided test, so we're going to stay in this box here. But it is significant because it's less than 0.05. If the Levine's had not been significant, we would have used the top row and we would have looked here, right? They're both significant, so it doesn't really matter. But I want you to know which one to look, because what's the difference? Here we have 22 degrees of freedom because we had 24 individuals. 1 degree, n-1 for the first group, n-1 for the second group, and we get 22 degrees of freedom. What's this? This is the adjustment. They adjust based on the degrees of freedom for this equal variance is not assumed. And you get really close. Your T statistic is the same. It's the degrees of freedom that change, and your confidence intervals change a little bit. So it's important to know where to look. Okay, and I just said this, we talk about the degrees of freedom. All right, so Cohen's d for two independent samples. That's another thing. We used to have to actually calculate this out. We would use an online calculator, but SPSS now gives it to us. It's auto-populated. Let me go back and show you. Here it says estimate effect sizes. We just leave that checked. All right. So now we can just go and look at our independent samples effect sizes. We want Cohen's d, and we want we want the point estimate rather, which is 1.333, and then we make our decision. So we have to come back here, and I showed you this again because you need these values in order to write it out. So step 4 is to state your conclusion. Here we conclude that the difference in these two sample means is significantly different. We would say that there is a significant difference in the amount of radiation in baby teeth of Pennsylvania and New York residents. And I would even add with more radiation in the Pennsylvania sample than the New York sample. And here it is in APA. T of the 15.9, I just rounded, well, I should have rounded to 16, but I kept it that way so I could show you that we're using the second row and not the top row. 3.27, which I rounded here. P is equal to 0.05, 95% confidence interval, and I got that from here, 3.9 and 18.4. Cohen's d is equal to 1.33, which is from the previous slide. And in AMA, you just make it a subscript. You don't put the spaces around. Capitalize P. Just kind of change the confidence interval a little bit. Cohen d is equal to 1.32. All right. So that's how you do an independent samples t-test. And let's remind ourselves, when we do an independent samples t-test, we're comparing the difference between two groups on some outcome variable. When we do a one sample t-test, we're just looking at one group against some hypothesized mean for their outcome measure. All right, let's do another one that's not in the book. The book data sets are so small, I want to use a real one. So this is something from my own, or actually I think it's from the BMI data set. I'm not sure. So is there a difference in height between males and females? What is our independent variable? Gender. What is our dependent variable? Height. So my null. The null is that the mean of 1 is equal to the mean of 2. So I could say the mean of males is equal to the mean of females. There is no difference in height between males and females. Eventually we're going to kind of fall away from doing the Greek only, and we're going to write it out in words. There is no difference in height between males and females. The alternate is that there is a difference in height between males and females. We're not saying where, we're just saying there is a difference, so it's a two-sided test. Okay, so I have a data set, and I move height over, and then I move gender over, and here I had to change my labeling because I don't have it as 1 and 2, I had it as 0 and 1. I leave effect size, I define my groups, I do that. Okay, and then I say okay, and I get my output. You can see that the males have a higher mean than the females, which is not surprising. Men are generally taller than women. I come in, first thing I do is I check my Levines, and what is it? It is not significant. So if it's not, I stay in the top row, and it's not, so I will stay in the top row. These are real data, I just wanted to make a note, and it's not uncommon to have unequal sample sizes. It's not a big deal unless they're really unequal, which is kind of a subjective call, but that's pretty close, so not a big deal. So we tested for the Levines, we see it's not significant, so we stay in the top row. That's a pretty big t-statistic. We have 397 degrees of freedom. Our one-sided and two-sided are the same. They're both highly significant. So we're going to say, is it significant? Yes, it is significant. There is a difference in height by gender. We look at our Cohen's d. We see that it's 1.05 or 1.1, and that's pretty big effect size. So we would say that there is a difference in the heights of males and females in this sample. And now I'm just going to, since I've shown you the AMA once, I'm just going to stick with APA. So T of 397 is equal to 10.5, P is equal to 0.001. Remember, actually I could have said P is less than 0.001. You never want to say it's 000, and SPSS stopped doing that. It used to just say 000, and now it puts the 1. 95% confidence interval, you get that from the other slide. Cohen's d is equal to 1.1. Okay, so that was our second independent samples t-test. Now, I want to look at paired or matched samples. Okay, what do you do when you don't have independence between your two samples? All right, so when we do that, we can do that. It's just a different test. So this paired samples t-test is what they call it in SPSS, compares two means that are from the same individual, object, or related units, such as measurements taken at two different times, for example, a pre-test and a post-test, with an intervention administered between two time points, or a measurement taken under two different conditions, for example, completing a test under a controlled condition and an experimental condition. Or you could say the same hospital, like I had way before in another example, the same hospital in March and in April. You know, it's just they're paired, they're from the same place. Measurements taken from two halves or sides of a subject or experimental unit, for example, measuring hearing loss in a subject's left ear and right ear. So when they're dependent, when they're the same person, we use this test. This test is also known as a dependent t-test and paired samples t-test. This is what SPSS calls it. A repeated measures t-test. You'll see it in different books, different ways. The variable used in this test is known as the dependent variable or test variable, which is continuous, measured at two different times or for two related conditions or units. Alright, so the null and alternative hypothesis, or the alternate hypothesis. The null is that the mean of 1 is equal to the mean of 2. The paired or repeated population means are equal, and that the alternate is that they're not equal. The paired or repeated population means are not equal. And we can do it like we talked about the probability at the beginning of this presentation. You could do it where the mean of 1 minus the mean of 2 is equal to 0, because if they're the same, you subtract them, you're going to get 0. But I like this way better. Okay, so let's look at the enrollment data set. Is there a difference in the overall sample scores from the first English test to the second English test? That's my research question. Our hypotheses are the mean of the English test 1 is equal to the mean of English test 2. There's no difference. Think about a teacher, right? You want your students' grades to get higher and higher and higher as they study more and do more of your work, right? So we want them not to be equal. We'd actually want the English test 2 to be higher than the English test 1, but here we're just testing that they're not the same. Okay, so let's look at our variable view. We have a bunch of variables here, and we have these types, right? We have numeric, date, string, etc. Some variables are strings, which mean words, and some are numeric, which are interval or ratio. Sometimes when you upload from an Excel spreadsheet, for example, or CSV file, you will get, these will be mislabeled. And so you have to check these. But we're looking at two continuous variables. So we could let's just consider which research questions we could ask based on the tests we've learned so far. A difference question could be, is there a difference in mass scores by gender? So our dependent variable is mass score and our independent variable would be gender. A paired samples question would be, and I've already said this in the hypothesis, but is the English 1 test different than the English 2 test? So the DV is the difference in English scores. You essentially subtract one from the other and do a one sample t-test on the difference score. So what is our IV? Right? We don't have an independent variable grouping variable, but our independent variable is time. The group is the same. The time each test was taken is different. Okay, so in order to do it, you go Analyze, Compare Means, Paired Samples t-test. You move English 1. You just click this little arrow and it'll pop it into this variable 1. You click English 2 and it'll bring it over to English 2. We leave estimate effect sizes, and this one's auto-populated. You have these options, but we're just going to leave standard deviation of the difference, and we're going to say okay. And then we evaluate our output. We can see that the mean for the first test was slightly higher than the second, but they're very close. So we have 82.7 and 82.2. We didn't ask for these paired samples correlations. We can see the sample size, the correlation coefficient, and the significance, but SPSS needs it to calculate the confidence intervals, so it just shows it to us. And then we look at these. This is the output we're interested in right here. We have our confidence intervals, our t-statistic, degrees of freedom, and our significance value. Since we're doing a two-sided t-test, we're going to look at the two-sided p, and we can see that we're not significant. It is not less than 0.05, so we do not reject the null hypothesis. And so we evaluate our effect size. You can see here that there are two different effect sizes reported. Hedges correction, referred to as Hedges G, and Cohen's D. Hedges is recommended when samples are less than 20. Both are interpreted just like the Cohen's, where small is 0.2, medium is around 0.5, and large is 0.8 or greater. All right, so then we would write it up in APA or AMA. We would say that there is no significant difference between English Test 1 and English Test 2 for this sample. T of 398 is equal to 1.12 rather. Degrees of freedom, 398 goes here. Confidence intervals we get from our lower and upper limits here. And then our Cohen's D is 0.06 from up here. And we're going to report the coins because we have a very large sample size. Okay, so just to kind of follow up with the tests that we've learned so far. We've learned 3 inferential statistical tests. We've learned a one sample, an independent samples, and a paired samples. But if we consider our research question, are we just trying to describe? If we are, then we're just doing descriptive statistics, not inferential statistics. These would be measures of center, measures of variability, measures of relative standing, frequencies, percentages, proportions, etc. Are we trying to compare? If we are, then we need to consider the number of groups. If we have one group, then we do a one sample t-test. If we have 2 groups, then we have to ask ourselves, are they paired or repeated? If they're not, we're going to do an independent samples t-test. If they are, we're going to do a paired samples t-test. The other way we could, other types of research questions we could ask, are we trying to measure a relationship between 2 variables? Or are we trying to do predictions? We'll talk about that later. Okay.